Here I've got the two waveforms shown on the oscilloscope, and I've used the cursors on the oscilloscope demonstrating to the students how to measure the phase difference between the two waveforms. In fact, they had done a pretty good job with this themselves, but I guess I've just come around to check this and clarify that they got the right answers. Anyway, compare results. So measuring that, and we find that we've got 256 microseconds of difference between the two, and channel 1 is in the yellow color and channel 2 is in the blue color, and you can see that channel 1, which represents the supply voltage, is happening earlier in time than channel 2. Channel 2 is the capacitive voltage, so channel 2 capacitive voltage is lagging channel 1, the supply, and that's what we saw on the board before. The capacitive voltage lags the supply voltage, and now we need to really look at how to do the maths on that, using that 256 microseconds and converting that to a angle in degrees out of 360. Alright, so we've taken the time now to go away and play in class and do the first part of the lab. But now let's check exactly against the results that we got. We calculated the duration, the period, for 900 Hertz, and we came up with 1.1111 milliseconds, 1111 microseconds. We're able to measure VC on the oscilloscope in peak to peak and convert it to RMS, 230 millivolts RMS. We've recorded it on the sheet. VS was 4 volts peak to peak, which is 2 volts peak times 0.707, which gives us 1414 millivolts RMS. And then we measured the time difference between the two waveforms using the oscilloscope, and we used the cursors. Students did a good job with that overall. When I checked their results, I measured at 256 microseconds. I probably could have blown the waveforms up a little bit more and spread them out a little bit more, but 256 seemed to be a pretty good result. I was able to use that 256 microseconds with the 1111 microseconds, and look, I might just move this other board across. So that would have been, and it is in fact, 256 microseconds divided by 1111 microseconds. Nice to have everything in microseconds because you don't need to use the exponent function on the calculator then. And that'll be times 360 degrees. So that's the time difference that we measured. That's the period for the frequency that we're working at. That's 360 degrees, and that gave me around about 83 degrees of separation. I think that's what I got. Let's just check. Yes, I got 83 degrees of separation. Other things that we're able to check here, I think that just about covers everything on that page. We'd already saw that that's the phase angle. That's theta 1, that's theta. And now let's just think about the results that we got and whether we can confirm those mathematically. We had a capacitive voltage of 230 millivolts RMS. We knew the supply voltage, but we do not know VR. This is VR. Don't forget VR here. This is VR. We don't know VR. So we can't use the tangent function to measure this theta 1. We have to use the cosine function. I'll show you what I mean. We don't know VR. So the cosine of theta 1 is going to be the adjacent on the hypotenuse, which is VC on VS. 230 millivolts on 1414 anti-cos, and we come down to 81 degrees. We measured 83 degrees, calculations say 81, but be careful, this is based on the measured VC. If I'd made a mistake measuring VC, those results, that result would not be exact, but it's pretty damn close. Actual unit values, so if we go ahead now, use the 900 Hertz, and we measure XC, come down at 177 ohms. We use the polar to rectangular, or rather rectangular to polar function on the calculator, and we put in those rectangular parameters, and we've got the resistor followed by the reactance. So 1K, 177 ohms gives me an impedance of 1016 ohms, and it also, as a resultant, that's the resultant, and the angle that we get, whoops, that would be theta, not theta 1, that would be theta 1 there. Theta, it gives me as 10 degrees, and then if I go 90 degrees minus that 10 degrees, I come up with theta 1. We got 83 degrees measured on the other board, and here it's saying mathematically 80 degrees. We have a deviation of 3 degrees, which is not too bad. I think that worked out okay on the day. So that takes us now to part 2 of the lab, and in part 2 of the lab we're going to transpose the two components. Now we'll put the capacitor at the front of the circuit, and we'll put the resistor in shunt, and then we'll take some measurements again, and that'll be the reverse of what we've done. So let's go ahead and do that, and then we'll come back and map that on the video again.